So I'm not going to recap last week's lecture, it's because you can just go and watch them again. But we spoke about the distribution of data. And so we were here, we're still in the counting beans and the statistics part of the unit, in the probability and sampling. So we spoke about probabilities, likelihoods of obtaining certain values and how we can establish that using PDFs and CDFs. And we looked at the normal distribution. We looked at it from a PDF perspective and from a CDF perspective, from a cumulative integrated perspective. And from those two, we got the moments that we wanted from the normal, from the PDF, and we got the median and quantiles from the PDF. We spoke a little bit about data sampling, about how it has to be random and independent and unconditional. And these are those summary statistics we got from each distribution. So now we know what a mean is and a standard deviation is, and skewness and kurtosis, and what a median is and quantiles are, and what distributions are, theoretical distributions exist and their parameters. We can move on to things like hypothesis testing, which is really what we're here for. So these were the different theoretical distributions we looked at. The student t, from that we get the t-test, the chi-squared, the gamma distribution, which is where we get the chi-squared test. The uniform distribution that requires no stats usually, and the normal distribution that gives us a lot of the parameters that we use to compare means. So that was the probability and sampling part. Now we're going to move on to statistical tests and correlations. And the last part of our statistics component will be time series analysis, which will come later. So how we sample and hypothesis testing, part one. So we can sample in a lot of different ways. I mean, like many of you will sample either a data set or remotely sensed data, or go out in the field and put out quadrats, or collect rocks, or whatever it is that you do, or collect some atmospheric measurements. But you're going to have a data set one day, and you're going to have to use that data set to test any hypotheses that you have made. So we're going to talk about data types first. So my Excel spreadsheet can be populated with all sorts of data. And so this was when we talked about different sampling methods. We're not going to focus on that now. But we can have all sorts of data in the spreadsheet. We can have data that once we've spoken about exclusively till now are continuous data. So these are the real numbers, what we call the real numbers. So which can be any value within a range of values. So I can have, a value of 1 or 0.5 or 3.2 or 400 or -8 or -16. Okay, so I can have a continuous range of variables. Or I can have data that is categorical. And in the categorical data, we mean discrete values, and nothing in between, or some attribute, not necessarily a value, but it's discrete. So it's not a continuous variable. It's then divided into things that are ranked, so ordinal values. So it's a scale of 1 to 10. Okay, so if I have a scale of 1 to 10, I know that 10 is better than 1. Or usually I have to tell people, how much do you love me? 1 to 5. 5 is a lot, right? So, 1 is a lot, 5 is a little, and that's where there's a lot of points of confusion and relationship breakdown. And we have a scale of 1 to 10. 10 is better than 1, but it doesn't mean that 10 is 10 times better than 1. This is not a continuous variable. It's ordinal, okay, by order. We have categorical values that are just nominal, okay? So I have calcium, magnesium, okay? So calcium is not bigger than magnesium. It's just different names for things, okay? It's a different, these parameters that I'm measuring are like something to do with the chemical composition of something. And then we have variables that are binomial. And there are the yes, no questions, true, false, dead or alive, land or sea, presence or absence of something. Okay, so these are the main types of data that we have. And really we're talking about things that are continuous versus categorical, and the statistical tests we use will really depend on what kind of data we have in our spreadsheet. So here's an example of a spreadsheet someone took. Okay, so we have some sort of bag number. Okay, so in different, these are the numbers of days those bags were out in the field. This is the zones those bags were out. So those zones are categorical. Okay, so these are the replicate numbers. So here we have some ordinal replicate number. Oh, actually, it's just a name, nominal. And here we have a variable that is a real number. Okay, so this is a continuous variable. The soil volume, the bulk density of the soil again is a real number. So a continuous variable, elevation continuous, root dry rate. Okay, so what we have here is an Excel spreadsheet, or if you like, in R, it's called the data frame. So what we have here is a data frame that is made up of lots of different cells. And each variable, the V, is defined. So we have different variables. Okay, so zone is a variable, replicate is a variable, dry bulk density is a variable. And I can identify any cell in this data frame using these coordinates of X, okay, the row number and the column number. Okay, so 1, 5. And because of the cell kind of idea, it's usually square. I mean, like it's always square brackets. So we have data. We know what type of data we have now. It's all in a spreadsheet or in a data frame. And now we want to go ahead and test whatever it is we want to test. So first of all, whatever it is we want to test, we kind of worked out before we went and gathered the data, right? So we have a hypothesis, because we're doing science. We are testing a hypothesis. We're not proving a hypothesis. We don't come at this in a biased kind of way. We're just testing this idea we have. And we have some educated guess of what we're expecting. So there's an aim to our sampling. And our sampling needs to be tailored to the aim. We often have a problem where we sampled without an aim, and then trying to make those samples fit the aim becomes harder. So it's always better to like kind of know what you're going to look for before you go looking. And then we have, we're going to look at the elements of a statistical test. What are the processes we go through? We're going to talk about the t-test first of all, and I'll give you lots of examples there, and then we'll talk about some other tests like the chi-square, the Wilcoxon rank test, and the ANOVA. So again, stats are actually quite easy to do. It's just a matter of knowing which test to apply to which conditions. So let's start with the plan. So the plan of going out and say you're doing your honors or you are creating a report for this place you work at. First of all, you want to know what your hypothesis is. So you start out by stating it. And you state it in a bit of a dichotomy. So you start with stating what the null hypothesis is and any alternative ones. So these two are stated in a way that they are mutually exclusive. You can't have one true and the other one true as well. So that you have to have one is true and the other, so thus the other one must be false. And then when you have, and we'll come back to hypothesis framing in a minute, but the next step would be to formulate some sort of analysis plan. How will I use my data, or how will I sample data? How will I use the data that I've sampled to evaluate the null hypothesis, to work out whether the null hypothesis is true or not. So I'll give you an example. I'm interested in climate change. I want to know if the distribution of some species of eucalypt today is different to what it was in the 1930s. I have data I can go collect in the herbarium. I go to the herbarium, I collect my data set, and my null hypothesis is that actually there has been no change in the distribution. Okay, that's usually my null one, is like that things are as they were. And my alternative is, well, actually, there has been a change in distribution, which maybe later I can attribute to climate. It's not straightforward. But I will formulate an analysis plan so I can sample randomly and independently these data sets from the herbarium for pre-1930s and post-1970s. And then I have my two populations. I have the old population and the new population, and I want to analyze if they're different or not. And that is the part where I will use a test statistic. So I have, in this case, this sounds like a t-test, but I mean, we'll come back to that later. And of course, once I've run the test, I need to interpret those results. So I'm going to apply some sort of decision rule, and we will often use something that's called a p-value, and that would be described in my analysis plan. And if my test statistic has a value that is unlikely to support the null hypothesis, I will reject it. So the aim of my scientific experiment or observation is to verify or reject a scientific hypothesis. So I'll give you a few examples here. Is X significantly different from X0? Okay, so that was like the climate change. I mean, like, is distribution different to what it was? Is X related to Y? Is the level of sedimentation linked to wave height in the coastal zone? So I can estimate that by some sort of correlation or that type of modeling, regression. And I can use it for discovery, so to detect a signal in my data. For example, I'm looking at long time series of temperature. Can I run some experiments on that data set to look at whether El Nino is an intensifying or changing frequency over time? So the elements of this statistical test are mainly to identify a null hypothesis. And by that, I choose a test variable, okay? And I look at the PDF of the test variable. So say I have, I'm interested in whether the giraffes of Kenya are different in height from the giraffes of South Africa. So I have an aim. My null hypothesis are that they are not different. If I take a giraffe from South Africa and measure it, and I take a giraffe from Kenya and measure it, and I didn't know which one was which, I would not find that they are different. Okay? And my alternative is, well, yeah, the Kenya ones are a different height to the ones in, I think I said South Africa. So I will choose some sort of test variable, height, okay, that describes my distribution. So I'll take the mean height, okay? And I will run a PDF of those two. And around each mean, I will find some sort of confidence interval. Remember, we spoke about those standard deviations and the quantiles. Okay, so my confidence interval was from 5% to 95%. That is the comfortable range I'm allowing around my mean. And then I will check whether that mean of the other giraffes, the ones from Kenya, falls within that confidence interval of what I'm confident in saying is the South African giraffe. Okay, and then I will have where the hypothesis is true, my null is true, or where it's false. Okay? So if they fall outside, my test statistics fall outside, it is false. Okay? So that is really just the bare bones of the statistical test. The null hypothesis, when we state it, and we actually do state it, we state it in writing, is denoted with a null, with a 0, right? So it's H0 or H null, if you say it like that. And that's usually the hypothesis that the sample observations are a result of pure chance. Okay, so any giraffe could be that height, the Kenya one or the South African one. There is nothing there. Okay. My alternative one, which is either HA or H1, because sometimes there's more than one alternative hypothesis, is that the sample are actually influenced by some non-random cause. In this case, a geographical, about geographical distance. So different climates result in different sizes of organisms. So I have an alternative hypothesis, and usually that's driven by theory or by an idea I had or some observation on another species, that this should happen as well, that the Kenyan and South African giraffes are not supposed to be the same size, okay, because they're from a different latitude, and we know that latitude affects the size of organisms. The thing to make note of is that we are really testing whether we can reject or accept the null hypothesis. Because there's more than one possibility for the alternative, we don't usually accept the alternative hypothesis, we reject the null. Okay? So it does not mean your scientific hypothesis is correct. All I know is that the Kenyan ones are different to the South African ones. So this was our normal distribution, okay? And we spoke about how we can have quantiles, okay? So the 95th quantile of the distribution sits, if it's in one tail, only to one side of the distribution, we have all of that 5% sitting in the larger values. Or more often, we use a two-tailed test, which means we are spreading that 5%, 2.5 on each side of the mean. So one tail entails that the H1, my alternative hypothesis is that the giraffes are larger than in Kenya. South Africans are larger than in Kenya. My two-tail just says, well, no, those means are not the same. The giraffes are different between the sides. And to have a one-tailed test, you really need to have some backing in terms of why you would expect only a one-sided result, which is why almost everything is two-tailed. But this is going to go into detail. We're not going to go into at this level. The last thing I'm going to touch on, and we're going to talk about it in more as we go. So the p-value, the probability value, you've seen this in the cumulative distribution function. This is the p that we talked about in the probability that x is of the population that is smaller than this p, or 1 minus that, right? So the p-value is the probability of our test statistic in this case to be larger than a certain value. Okay, so this is how we would measure this. I don't want to, this is getting a bit complicated to explain because we haven't done this yet, but I want you to remember the p-value. We, in biology, environmental science, geology, these sciences, we tend to use a p-value to determine differences that is smaller than 0.05, so 5%. There are disciplines that use a different value. Okay, so this is a bit arbitrary, but this is what we've stuck with for a few decades as a society. And this is our rejection point. So our null hypothesis is tested with the test statistic. We get a p-value, the probability that the test statistic is different to our test statistic is different to that population of test statistics around the null hypothesis. So if it's really different, it means the p-value will be smaller than 0.05. So the p-value is low, the null must go. Okay, so that's something to remember when we come back to p-values. Just try to memorize that for yourself. Okay, thank you very much.